Hello, everyone. We're back, and we are here to talk about trig graphs this time. So, in the previous lesson, we learned what the trigonometric functions are, and that's sine, cosine, tangent, cosecant, secant, and cotangent. We learned what they are, but they really just come from understanding terminal points, which I guess was the lesson before that. So we understand the unit circle, we've defined what the trig functions are. We really haven't seen what they're used for yet, but we'll get to that pretty soon. For now, we want to talk about their graphs. What do the graphs of these functions look like? All right, so let's go ahead and get started. Trigonometric graphs. So I'm going to start by telling you that this lesson is just going to cover the graphs for sine and cosine, and we'll have another lesson that covers the other trig function graphs. So in previous lessons, we've said t equals pi over 2 has terminal point. Do you remember what this terminal point is? We want to get pretty quick at these for some of these common values. 0, 1. All right, and that comes from quick scratch work unit circle. And we say if we go pi over 2 around the unit circle, starting from the usual spot, going counterclockwise, it takes us up here. We know the unit circle has a radius of 1, so we know that this is up here at the point 0, 1, right? We also said that t equals 2.5 pi. That was an example that we did probably 2 lessons ago. And this has terminal point. 0, 1. Same terminal point, even though it's a different t value. I mean, these t values are different. Can we see this on a unit circle? Well, yeah, any terminal point can be visualized on a unit circle. So let's see, what would 2.5 pi look like? I guess we know that if you go 2 pi, then you've gone around the unit circle once. So really, what 2.5 looks like is you go around the unit circle once, and then you go an extra 0.5 pi to end up here on the unit circle at that same point. We did an extra lap around the unit circle to wind up at the same point. Now, using what we know, about trig functions, this means that sine of pi over 2, remember that would be the y-coordinate of the terminal point, so that's 1. Cosine of pi over 2, that would be the x-coordinate of the terminal point. It equals 0. Sine of 2.5 pi is also going to equal 1. Cosine of 2.5 pi is also going to equal 0. Now, in this little example, I showed you pi over 2. That's one of the common t values that we might use. And then I showed you what it looks like if we basically do one extra lap around the unit circle and then wind up at that same point. You could also imagine, what if we did 2 extra laps around the unit circle and still stopped at that same point? Or what if we did 3 extra laps around the unit circle and wound up at that point? Or 100 extra, right, revolutions around the unit circle and still stop at that terminal point? You would still have the same sine and cosine of 1 and 0. So it seems that as functions, the function sine and the function cosine, it seems like they're going to keep getting these repeating values. I'll tell you that sine of 4.5 pi is going to be 1. Sine of 6.5 pi is going to be 1. That doesn't mean that it's always 1. It just means that it gets to 1, some other stuff, then it's 1 again. All right. We have a name for this kind of behavior, this sort of repeating behavior. We say sine and cosine are periodic. They are periodic, meaning they are periodic functions, and that they have period 2 pi, meaning that sine, let's move this up a bit, that sine of t plus 2 pi is going to equal sine of t, and cosine of t plus 2 pi is going to equal cosine of t. I'll give you a chance to see that. So it says if you take any t value and then you add 2 pi, you still get to the same terminal point, so you still have the same sine value and cosine value. Now, this section is called trigonometric graphs. Are we talking about trigonometric graphs? Not yet. What we've done so far, we're just introducing this idea that these functions are periodic. And this is going to help us in what we're about to do. We're about to start trying to come up with the graph of sine and then cosine. Let's start with the graph. Let's say graphing sine. We want to figure out what the graph looks like. I don't want to just tell you right away. I want us to kind of figure it out. How about we need a quick little unit circle to reference. The unit circle itself, I want to be extra clear. The unit circle with a bunch of stuff labeled, that is not the graph of sine. Okay? The unit circle is its own thing, but it's going to help us. So what I'm going to do is just leave it there for now, and we'll add to it as needed. Sine is the y-coordinate of a terminal point, right? Based on the unit circle, what do you think is the largest y-coordinate we're ever going to get? It's going to be up here, right? The largest y-coordinate you'll ever get on the unit circle is 1. Because if you go any higher than that, you're not on the circle anymore. That happens at a t value of pi over 2. What's the lowest value that we're ever going to get on the unit circle? That would be at the bottom. And this would be at the point 0, -1. So -1 is the lowest output that we would ever expect to get from sine. And that happens at a t value of 3 pi over 2. I'm going to go ahead and zoom in on this a little bit. We're going to work on this part for just a moment. How about this? Does sine of t ever equal 0? Yeah, it does. The y-coordinate of a terminal point does equal 0 in 2 places. In fact, it happens here at 1, 0, which corresponds to the t value of 0 or the t value of 2 pi. You could think of it both ways. They both get us to that same terminal point. There's also another place over here at the point -1, 0, which happens to correspond to t equals pi. Sine of pi is going to equal 0. Okay, so this is enough for us to get started with. Let's zoom out. And now to the right, I want to set up a graph where we're going to actually draw sine. I know that the highest that it will ever go is a height of 1. The lowest it will ever go is a height of -1. So I'm going to set up my picture according to that scale. There's 1. There's -1. And this is the y-axis. And what would the horizontal axis be? Well, so far in our discussion of sine, cosine, and the others, we've talked about them as being functions of t, right? We say sine of t. So I'm going to say the horizontal axis is the t-axis because that's the variable. And what we are working on is graphing sine. So ultimately, this is going to be a graph of, do we want to say y? Is that going to be confusing? We could say y. It's fine. Y equals sine t. You could say f of t if you want. Either way. Now, what I'm going to do is I'm going to say we need to figure out, I labeled some things on the y-axis, the max height of 1, the min height of -1. What are some t values that we might be interested in? I know that when we go around the unit circle once, we've gone a total of 2 pi. So maybe I'll say 2 pi is, you know, we want to kind of include everything up to 2 pi at least in this picture. So let's do that. And I'll label some things in between. If that's 2 pi, then I guess this would be pi. Let's get pi over 2. 3 pi over 2. And I'm going to put little marks kind of in between each one. So what are these marks? I mean, this first one would be pi over 4. Right, because it's halfway to pi over 2. Next one would be 3 pi over 4, and so on. I just don't want to label all of them. It's going to get messy. All right, I think we're ready to actually plot some points. So, do we know any points on this graph? Let's start at t equals 0. When t equals 0, what is sine? We could even set up a little table if you want. All right, we don't have a ton of room, but here, scratch work. What's sine of 0? Sine of 0 is the y-coordinate corresponding to the t value of 0. So the y-coordinate is 0, 0. So this means that the graph that we are making includes the point 0, 0. Put a point there. Let's move on to sine of pi over 2. What's sine of pi over 2? You can tell from our unit circle that the y-coordinate is 1. So this is 1, which means the graph that we are making includes the point pi over 2, 1. On this graph over here, let's plot the point pi over 2, 1. And I expect that that's the highest that this graph is going to go. We're going to run out of scratch workspace, but let's do one more here. Sine of pi. Sine of pi, we've gone around the unit circle. We wind up here. We look at the y-coordinate. The y-coordinate is 0. So the point on the graph that we are going to put is pi, 0. On this graph, it is here. So far, we've plotted 3 points on the graph of sine t. There are lots of in-between points. We'll talk about some of them. Let's continue this strategy without doing the scratch work at the bottom. Let's say, how about at 3 pi over 2? What is sine of 3 pi over 2? It looks like, according to the unit circle, it would be -1. That's down there. But I expect that that's the lowest that this graph is going to go, because the unit circle never goes any lower. What is sine of 2 pi? Well, we've said that when you go 2 pi around, you get right back to where you started at this terminal point, and the y-coordinate is 0, so we have the point 2 pi, 0. Now, we've plotted 5 points, and they are on the graph of y equals sine t. It looks like if we imagine that there are points in between, I guess it starts at the origin, it kind of goes up here to this point, down here to this, keeps going down, then goes back up. Maybe it's doing like a zigzag up and down or something. Let's fill in a couple of the in-between points. So what about this right here? What is the point corresponding to halfway in between t equals 0 and t equals pi over 2? Right there. That would be the t value pi over 4. At the t value pi over 4, we have the terminal point, square root of 2 over 2, square root of 2 over 2. So, on our graph of sine t, that would be going with this t value, and the y value is square root of 2 over 2. Where is square root of 2 over 2? So, okay, I'll continue the scratch work, I guess, a little bit. Square root of 2, I know that that's approximately equal to, you don't have to know it exactly, but I know it's around 1.4. So, the square root of 2 over 2 is approximately equal to 0.7. So when I draw this point, it's going to be at pi over 4, comma, 0.7. How does that look? How about this point over here? You can figure out what t value this would correspond to. I guess this would be 3 pi over 4. And same y value, right? Like if I did sine of this, I get the same y value. So I'm just going to put that on the graph. Here's 3 pi over 4. The y value is also around 0.7. There's some other digits, but that's close enough. All right, altogether we've got 7 points plotted on this graph. There's also in between ones. We could look at pi, t equals pi over 3, pi over 6, 2 pi over 3, right? Like you could come up with other points to kind of try to start filling this in more. But what I'm planning to do is just get a couple more points on this, and then I'll show you how the points are all connected. Down here would correspond to this t value, and we're going to get negative root 2 over 2, comma, negative root 2 over 2. Negative root 2 over 2 would have to be about negative 0.7, which is about here. And we also get another point right around here at that same height. So altogether, what do we have? About 9 points here. But like I said, you could imagine all the points that are in between. Also, you could keep going to the right. Like, what if I went further after 2 pi? If we kept going, we would start getting the same points again. Like, for example, here's 2.5 pi, right? We said sine of 2.5 pi was 1, so we'd have a point up here. We'd also get this point here, this point here. All right, I think I'm ready to connect these dots. I'm going to connect the dots and show you that this actually connects into a nice smooth curve. Why do we just connect these dots? It's because all of the in-between values are also there as part of the graph. We could also have a point about here, here. And that's a pretty good graph of sine. Graph of sine looks something like that. So I'll have to get a fresh sheet of paper and move some of this. But that's a good graph of sine. I'm going to say graph of sine zoomed out. What if we zoom out? Because I set this up to, have kind of a certain region we were focusing on. I want to show you that if you were to have this be 1 and -1, and then maybe you just look at like pi, 2 pi, 3 pi, 4 pi. We're using multiples of pi because those seem to be kind of the important points. All right, so what would we get? We would get kind of the picture we drew here that kind of goes up and down by the time it gets to pi. Up and down by the time it gets to pi. And then it goes down and back up by the time it gets to 2 pi. Like that. All right, so this right here, earlier we said sine is a periodic function and that it has period 2 pi. We said that it has period 2 pi. So this is considered, this right here, this has a length of 2 pi, and that is considered 1 period. That is 1 period of the function, okay? What I want to tell you is to draw the rest of the function because sine is just going to repeat itself. Because this curve is just going to repeat itself again and again. The way that you could think of it is you draw 1 period and then grab this and copy and paste to the right and again and again and over and also to the left. Copy and paste, copy and paste, copy and paste. This idea that you can copy and paste the first period of the function over and over, that is basically what it means to be a periodic function. It means there's a repeating shape, could be a repeating curve. We'll say that's enough. And that's what I wanted to show you. Maybe I'll darken in like the first period just for emphasis. Now, if you were asked to graph a picture of sine, how much of it should you draw? Well, I would say the answer is you should draw at least 1 period. If you draw any less than 1 period, then you haven't really drawn the whole shape. So draw at least 1 period, preferably a little bit more, like we did on this first picture. I drew 1 period and then a little bit more to indicate, that it's going to repeat and keep doing that shape. You don't necessarily have to do, what did I do? 1, 2, 3, 4, 5 periods. You don't necessarily have to make that many. But I want to show you this. It keeps going up and down like this pattern forever. Now, that makes this type of function different from some other functions that we've worked with in algebra and pre-calculus because it has this repeating pattern. Polynomials never do this. Exponential functions never do this. Logarithmic functions never do this. Linear functions never do this. Trigonometric functions are probably the first periodic functions you've seen. And because they keep repeating themselves, that makes them useful for certain real-life applications. For example, sound waves. Or how about water waves? How about something that's vibrating up and down like a spring? So those are some of the applications that we'll see. Radio waves, anything that waves up and down that might fit this kind of shape or something like it. Now that was our discussion of the graph of sine. And you don't have to recreate the graph of sine from scratch by using a unit circle every single time. That was just because it was our first time doing it. Now we've kind of figured out that this is what the graph of sine looks like, and it's okay to just remember that this is what the graph of sine looks like. Skip a lot of the scratch work, and if I ask you to graph sine, you can graph sine, and you can do this kind of graph also. One thing to kind of remember is that sine passes through the origin because sine of 0 is 0. Remember, the highest it goes is 1, the lowest it goes is -1, and it keeps going up and down between that. Also, when you draw a graph of sine, it should be curved. It should be like a nice, smooth, gentle curve up and down, not like a zigzag like a lightning bolt or like the letter V. It should be curved. Okay. Let's draw the graph of cosine. And for cosine, we're going to spend less time on it because a lot of what we just said, the same kind of ideas apply. So let's work on graphing cosine. I wish we could fit, maybe, can we do this? I wanted to try to fit the same unit circle on the screen. Maybe we can just barely see that. How about this? I'm going to assume that you've got the unit circle in your notes. I might point up at that, but if it gets a little bit off the screen, then I'm going to assume that you've got a unit circle in your notes at this point. All right, we will refer to it. I would like to graph cosine similar to how we graphed sine before, but we'll go through it a little quicker. Here's the max height of 1, minimum height of -1. So why did I say that it has a maximum height of 1 and a maximum height of -1? I'm looking at the unit circle and I'm thinking, what is the maximum cosine value that we ever get? That would be the maximum x coordinate on the unit circle. It seems like the furthest to the right that we ever go is 1. So the max x value is 1. Max min x value is -1. All right, we are trying to draw a graph right now of y equals cosine t. And if it bothers you that I'm using y, like you might look at this and say, wait a second, I thought sine is the one that equals y and cosine is the one that equals x. If that bothers you, let me explain. I'm using y in a different context here. I'm using y because usually when we graph, we prefer to call the vertical axis the y-axis. We draw graphs like y equals e to the x, y equals x squared. Every time we draw something, it seems like we call it y equals something. So I'm calling this y. However, if you don't like that, you could call it f of t. That would be perfectly fine. F of t equals cosine of t, because it is a function of t. But it's also okay that we're doing this relabeling if we understand that in this context we're doing it so that the vertical axis is the y-axis. All right, what's cosine of 0? Look at your unit circle. Cosine of 0 is 1. So we have the point here. Cosine of 0 is 1. So we have the point 0, 1. That's up here. This is already different from the graph of sine. Right? Oh, maybe I should go ahead and label some like pi and 2 pi and stuff like that. Let's do 2 pi here. Pi. These seem like they were useful for the previous ones, so maybe they'll be useful here. Okay. Already different graph from what we had for sine. Okay. What is cosine of pi over 2? Cosine of pi over 2 equals. So I'm looking at my unit circle, and it looks like the x-coordinate is 0, so that would give me a point here. point. All right, so at this point, I think I'm going to stop doing the little scratch work off to the side and say we can just kind of do that in our head looking at the unit circle. What is cosine of pi? Cosine of pi seems to be -1. So down here. Cosine of 3 pi over 2 seems like it is 0, because that's the x-coordinate of that terminal point. Cosine of 2 pi seems to be 1, because that's the x-coordinate of the terminal point. So what's happening? Are we getting like a U-shape, like a parabola or something? Well, how about this? Let's fill in a couple more points before we decide. Pi over 4 is one of the common values. What is cosine of pi over 4? That would be the square root of 2 over 2, which we said is about 0.7. So I'll put that here. Cosine of 3 pi over 4 is going to be about -0.7. So now I'm thinking this doesn't really look like a parabola anymore. Let's fill in some more points. You're going to get this point here, this point here. Oh, let's go out to 2.5 pi again. 2.5 pi. What was cosine? We said cosine of 2.5 pi was 0. Remember that? A few minutes ago? All right, look at all these points. See what pattern we're getting? In a way, it kind of does look like the graph of sine, but not exactly. I'm going to connect these points with a nice smooth curve. So that's part of the graph of cosine, and that's a pretty good picture. Compare this with the graph of sine. I mean, you could just look at the zoomed out version of sine that we had a minute ago. So what's different about it? It does wave up and down, and it's going to wave up and down continuously, repeatedly, forever. So we could also draw like a zoomed out version if you want. I'll kind of, I don't know. I feel like we'll do it quickly here. Zoomed out. Why not? Like, what does one period of this look like? So max height of 1, minimum height of -1. Let's say pi, 2 pi, 3 pi, 4 pi. I was going to skip this, but, you know, it's good to see it zoomed out for the periodic behavior. Notice that I'm not, on the t-axis, I'm not labeling 1, 2, 3, 4, 5. I'm going with pi, 2 pi, 3 pi, like multiples of pi, because they seem to be useful for this. Okay. We could draw the part that we had in our first picture of cosine. So I guess we have a point here. We have a point here. Here. Like this. That's everything from 0 to 2 pi. So you could do the same thing again and say this length here is 2 pi. You could say that this is 1 period, right? If I take this part of the picture, let's make it a little darker just to emphasize it. If I take this part of the picture and I say I'm going to take this and copy and paste it to the right and put a bunch of copies of it to the right, and then I'm also going to put a bunch of copies of it to the left. So what's going to happen? Something like that. something like that. So now if you compare this, I think, can we fit these both on the screen? Probably not. But if you compare this zoomed out picture of cosine with the zoomed out picture of sine, they do look very similar, don't they? They both wave up and down. Max height of 1, minimum height of -1. They wave up and down with the same kind of shape forever. In fact, if we were to draw them at the same exact scale, I don't think I drew these pictures at the same exact scale, okay? But if you did, you would see that the only difference between these pictures is that the cosine picture seems like it's been shifted horizontally compared to the sine picture. The sine picture passed through the point 0, 0, the origin, right? The cosine one did not. It passed through the t-axis, pi over 2 units over. So different t-intercepts. But the overall shape is the same. It's just been shifted slightly. Sine and cosine are very similar. Pretty cool. Pretty cool. Now, you'll want to know what the graph of sine looks like and what the graph of cosine looks like. But you're probably not going to get asked to just draw a graph of sine. Like, I probably won't say, here's a problem, draw the graph of sine. That would be considered a little too easy. Instead, what you might get is some graph transformations, where you have to start with sine and then do something to it, or start with cosine and do something to it, shift it, scale it, flip it, all of that. So here's what we're going to do. Talk about graph transformations. I'll show you a couple of problems, and I'll talk us through these because this is new for us, I guess. But you should know graph transformations for other functions, and the same thing applies here. So I would like to talk about these functions, and for now, this is the first time I think that we've done this. I would like to change the variable, the name of the variable, the label of the variable. I'd like to start calling it x. Okay? We've been calling it t. We've been calling the variable t. But a lot of times in math, when we deal with functions, we like to call things f of x. We like to call things y equals f of x, So I want to say, let's graph f of x equals 2 plus sine x. And let's graph g of x equals negative cosine x. And I'll do these for us. I'll talk us through this. Up until now, we've been calling the variable t because we were talking about these t values as this concept of, a t value is how far around the unit circle you go. But we're graphing, and I would really like to be able to label the x-axis and y-axis as x and y. So I'd like us to be comfortable with thinking of the sine function as possibly being labeled as sine of x. Cosine could be cosine of x. All right, so part A. What do? Let's start with y equals sine x, which we drew a picture of earlier, but I'm going to draw another picture of it now, and then we'll figure out what kind of transformation we're doing to it. So I know that we need at least one period if we're going to get any kind of accurate shape. This is not the final answer. This is not the final picture, so it doesn't have to be perfect. Try to make sure our final picture is good. But I think this turned out pretty nicely. All right, now let's try to do a graph transformation to this. Oh, and I'll label the x-axis and y-axis, x and y. So what transformation do you think we're doing by having that 2 there? I'm going to write up here where the problem is that this is the same as saying f of x equals sine x plus 2. And having a plus 2 on the outside means shift up 2 units. So that's what we want to do. We're going to take the graph of sine x, shift it up 2 units. That's no big deal. The graph of sine typically has the lowest point at -1 and the highest point at 1. But if we shift everything up 2 units, let's leave some vertical space for us to do that. Well, the maximum height was 1, but now if we shift it up 2 units, the maximum height is going to now be 3. So let's make sure this graph goes up to at least 3. All right, do you agree with that? We need to go up to at least 3. How about this? The original graph of sine typically passes through the point 0, 0. We shift it up 2 units, it's going to pass through the point 0, 2. That's a start. I know that when we shift a graph up or down or left or right, it still retains its same original shape. It's just been, moved around, translated on the XY plane. So let's see. I'll put 2 pi here, pi, negative pi, negative 2 pi. So we could still have the same up and down curve. By the time it gets to 2 pi, it's back where it started. So we go something like this. This looks pretty good. And this is a graph of f of x equals 2 plus sine x. It's the graph of sine, but it's been shifted up 2 units. Not a big deal. So you should be able to handle problems like that. You can double check that the highest point on my graph is now 3. That makes sense. The lowest point on my graph is now 1. Why is the lowest point on my graph 1? It's because the lowest point on the original graph was -1. So you add 2 to shift it up. I think everything here makes sense. Let's work on part B. How about this? I'll ask you to try part B. Take a minute, maybe pause the video, see if you can start with the graph of cosine and then do the transformation to get the graph of negative cosine. All right, so I'm going to start with y equals cosine x. Maybe you paused the video and tried this. It's good practice also just for drawing the regular graphs of sine and cosine, to draw them each time we do this. Let's go out to 2 pi. Let's go out here to negative 2 pi, negative pi, positive pi. And typical graph of cosine only needs to go up to a height of 1 and down to a height of -1. All right, there's my setup. Remember, the graph of cosine passed through a y-intercept of 1. You could remember that it has the same overall shape as sine, but that it passes through a y-intercept of 1. And by the time we get to 2 pi, it's back up there. By the time we go to negative 2 pi, it's back up there. It reaches its lowest point in between, so it goes something like this. Oh, by the way, when you draw trig functions like sine and cosine, make sure you draw arrows at the left and right ends of the picture. The arrows are there. Like, don't just stop. All right, watch this. Don't just stop here. Don't just be like, there's a point, stop, I'm done, it hit a wall. No, draw draw arrows to indicate that it does keep going. Okay. What does negative do? That's okay. Negative is a transformation that, so we want g of x equals negative cosine x. The negative is outside, so this means we're going to flip vertically. We're going to reflect about the x-axis, right? Reflect across the x-axis means that the x-axis is going to sort of act like a mirror, and we want to draw the reflection that you would get when you reflect through the mirror known as the x-axis. So instead of, well, let's set up the same kind of scale, I guess. It's not going to be any lower or higher. It's going to be kind of the same overall size, so we can use the same scale. That'll be nice. All right. Instead of passing through the point 0, 1, that point has been flipped. It's now down here. All the ones that were at a height of 1 are now at a height of -1 down here. All the points that were at a height of -1, they get flipped, and they wind up at a height of +1. See how I do this? I kind of draw a few points, and then I'm going to fill in the overall shape. The points that were at a height of 0, when I flip those, they stay at a height of 0. Because, you know, what's the negative of 0? It just stays right where it is. All right, that seems like that's enough to draw a nice picture. So connect them with a nice smooth curve. Try not to do like sharp angles, like sharp zigzags. Try to make it look like it's a gentle curve, like a roller coaster going up and down. Arrows at the end to indicate that it keeps going. We flipped it. We did it. Look, there's the original picture, and then we vertically flipped it. That's a good answer. That's the graph of g of x equals negative cosine x. I like that. Okay, I have one more that I want to show you. Let's move this up. One more thing for this section. Note. We may work with functions such as y equals a times sine k x minus b, and y equals a times cosine k x minus b for some constants. There's a bunch of constants, right? A, b, and k, with k being positive. Now, when we do this, we say the curve has amplitude, absolute value of a, period. You know how we said that sine and cosine have a period of 2 pi? The effect of having a k on the inside is it's going to change the period from 2 pi to 2 pi over k. And we say that it has phase shift b. Now, for now, For now, we'll have b equals 0. More about this in a later section. I'm basically introducing right now these variations on sine and cosine that have a bunch of constants involved. And we're going to revisit it later. In fact, when we revisit it in a later section, we're going to be using this for some word problems, for some things that wave up and down. Okay, but for now, we could look at these expressions or these functions, and we could say, all right, x is the variable, y is a function of x, right? These other things are constants. We could say that these are really like graph transformations. Having an a out front, having a k attached to it, having a minus b, like they all perform different graph transformations. So what I'd like to do for this section is I'd like to show you one example, and then later, in a later section, when we revisit this, we can go into a little bit more detail about these concepts of amplitude and period and phase shift. All right, so don't stress out about them too much right now. I just want to show you an example of graphing. So we're going to do -2 sine of 1/2 x. I'm going to talk us through this, but I will say, note, this is y equals a times sine k x minus b, where a is -2, k is 1/2, and b is 0. Also note, amplitude is supposed to equal the absolute value of a, so in this case it equals 2. Absolute value of -2 is 2. The period is 2 pi over k. Okay, 2 pi over 1/2 is 4 pi. And the phase shift is 0 in this case. So this was kind of a side note. I want to actually focus on graphing this, but at least we did address that this is a function in this form for this particular constant a, this particular constant k, and this particular constant b. Now we'll graph this and figure out what this looks like. Just like the previous two problems we did, it helps to start with a basic graph of sine or cosine. I'm going to start with the basic graph of sine, and then we'll figure out what the 1/2 is doing and what the -2 is doing. All right, so draw this a little quicker this time because we've been drawing this a few times today. -pi, -2 pi. All right, we started with a graph of y equals sine x. Looks good. Which thing should we deal with first, the 1/2 or the -2? Well, and you could also ask, does it even matter which one we deal with first? Order of operations tells us that the 1/2 is on the inside and should be dealt with first. Now, how do I know that? It's because it's sine of 1/2 x. Now, there's no parentheses here, but remember when we first introduced sine, I said that the parentheses were optional. I'm going to draw the parentheses here, I think, right now, in blue. Parentheses, parentheses. Those parentheses are optional, but when we write them, it helps us see that order of operations tells us to do the thing in parentheses first, so I'm going to deal with the 1/2 first. Now, when you have a constant in parentheses inside a function next to the x, do you remember what kind of graph transformation that is? It's not a shift to the left or right. It's not a shift up or down. It's not a flip. It's something else when you have a constant being multiplied times x. Because I just want to draw that for now. So I want to turn this into I want to turn this right now into a graph of y equals sine 1/2 x. And then we could deal with the -2 in the next step, okay? And the 1/2 on the inside, I'll tell you, means that there is a horizontal stretch. If you're ever not sure, if you ever don't remember, I mean, I guess you could set up like a table of values. Be like, I don't remember if this means to squish the function or if it means to stretch the function. You know, am I squishing it into half of its size or am I stretching it by a factor of 2? This is stretching it by a factor of 2. So we could go out to about 4 pi, maybe. Maybe that would be a good idea. That means 2 pi is here, 3 pi is here, -4 pi. And now instead of, well, we actually wrote over here in the side work, I said period equals 4 pi. And you should know that the shape of the graph takes up 1 period. So actually that makes sense that this is a horizontal stretch. And that is why the period is going to be twice as long as it usually is. Instead of a period from 0 to 2 pi, we're going to start at the origin. It's going to have to go all the way to 4 pi before it would repeat itself. These two graphs that I drew, they don't really look that different at a quick glance, but they are quite different because the x-axis is labeled out to 4 pi here. Like the first picture crosses the x-axis at pi, the second picture does not. You know, so these are quite different. We did stretch it horizontally, but just most of that is just shown in the different labeling on the x-axis, I guess. We've got one more thing to do, don't we? We have the -2 out front. This problem had a -2 out front. So I want to take this, and I would like to turn this into a graph of y equals -2 sine of 1/2 x. So what is the -2 going to do for us? It's going to do kind of two things at once, isn't it? The negative out front means vertical flip. And what else? The 2. The 2 means scale vertically by a factor of 2. All the y values are getting multiplied by 2. So now we'll draw the final answer. Ordinarily, the largest value that sine has, we said that ordinarily the highest that sine goes is 1. But because of the 2 out front, I'm going to make sure that this goes to -2 and +2. We're going to make sure this picture goes out to 4 pi at least to get at least 1 period over here. So that would mean this is 2 pi, 3 pi, and pi. And then we'll do the same thing here. This is our finished picture for this problem, so we want this final picture to look pretty good. We labeled the x-axis, the y-axis. We labeled a bunch of numbers on each axis. And now, okay, let's work on taking the previous step, flipping it vertically, and multiplying it by a factor of 2. If you want, you could split that into two different steps, but I think we're okay to do this in one step. What happens to 0, comma 0? It stays where it is. Because if you flip it across the x-axis, it's on the mirror, you know? Okay. Maybe we take maybe we just like take a couple of points to help guide us. So like this point that's here at pi, comma 1, it's going to get flipped vertically and scaled by a factor of 2. So it's going to wind up down here. See what I did? Then at 2 pi, we have a point that stays at 0. Next, let's work on this one. This point was at 3 pi, comma, negative 1. It's going to get flipped vertically across the x-axis to appear here where I'm pointing. But then it's also getting multiplied by 2, so it's going to actually wind up here. And we got a point over here at 4 pi. So overall, the shape that we're getting kind of feels like the same overall shape, but the scale is really quite different. It's going up to a height of 2. Here, we'll fill in some more of this. All right, I think this looks good. I think it looks good. So do you see that this is pretty different from the original graph of sine? If we compare it to the previous step, or even if you compare it to the original graph of sine, what do they share in common? I guess they're both periodic functions. They both pass through the origin. But this one has been flipped vertically, scaled by a factor of 2, stretched horizontally by a factor of 2, so that instead of one period going from 0 to 2 pi, one period has to go from 0 to 4 pi. So that's a good final picture of this function. I want to show you two things on this picture before we call it a day. Before we call it a day, I want to show you two things. Okay? One thing is that as you go from here to here, this length is 4 pi because the period is 4 pi. All right, it takes that much to get one period, and we kind of saw that in the little scratch work that we did above. I want to say something about amplitude. What does the amplitude mean? So basically, here's the highest value, and here's 0. And what's that height? That height is 2, isn't it? So the amplitude of 2 can be seen in the final picture because it's not, we wouldn't really say that from the highest point to the lowest point is 2, because actually from the highest point to the lowest point would be a distance of 4. But from the highest point to the middle, from the highest point to the middle is a height of 2, and that is what the amplitude represents. In the usual unaltered sine function, you could say there's an amplitude of 1. From the highest point to the middle is a height of 1. But this one was modified because of the negative 2 out front. All right, so we'll be finishing up here. I just wanted to say that. There is some significance to the amplitude and the period. I said not to really worry too much about the phase shift right now. You could do a problem with phase shift, though. Phase shift is basically going to be a horizontal shift. Not that big of a deal. So that was our section on trig graphs. And, you know, we basically derived what does the graph of sine look like and what does the graph of cosine look like. We figured it out by referring to a unit circle. We discussed the idea that they are periodic functions, that they keep repeating themselves forever. And then we looked at some graph transformation problems, and you might see some problems like that where you have sine or cosine, and maybe you have to scale it or flip it or shift it, things like that. Now, you might be saying to yourself, this section was called trigonometric graphs. We only talked about two trig functions. What about the others? What about tangent? What about secant, cosecant, cotangent? We left those out. And the answer is those are going to be the next lesson. The next lesson is going to be more trigonometric graphs, and we will look at those four. And those are going to look quite different from sine and cosine. So we save those for a separate lesson. Okay? All right, so thanks for watching, and I'll see you next time. Take care.